The next periodic trend we want to talk about is something called ionization energy. So ionization energy is the amount of energy required to remove an electron from an atom in its gaseous state. So if I take some random element X, right, there's no element X, it's just a generic writing here. If it loses an electron, it goes to an X plus 1. It forms a cation. The amount of energy required to remove that electron, that's going to be IE1, ionization energy 1, energy required to remove that first electron. If I then take that cation and remove a second electron, it's going to be IE2, ionization energy 2. It's always going to be harder to remove a second electron than the first. The more electrons you move, the harder it gets. Why? Well, fewer electrons means less repulsive forces. That stabilizes the ion. Those electrons get pulled closer and closer together. They go to a lower energy level. It's going to then take even more energy to pull them off. Okay, so that second ionization energy is always going to be greater than the first one. It's always going to be more difficult to remove the second one than it is the first one. You can go on and on. It's always going to be more difficult to remove the third one than the second one, the fourth one than the third one, and so on. Okay, if we look at a table of this, we've got a table of elements and their ionization energies. We've got from IE1 all the way to IE10. Okay, if you notice, the next ionization energy is always greater than the previous one. It's always going to be larger. That's always true. The other thing to notice here is that little blue area that's got the core electrons listed. If I start with lithium, its ionization energy 1 is 0.52. Well, that takes me to a lithium plus 1. What's the electron configuration for lithium plus 1? Well, it's helium. I've now got to that stable noble gas core. It doesn't want to give up another electron. Now, I can force it to give up another electron, but that's why there's a sudden jump from that 0.52 to the 7.3. It suddenly becomes more difficult to remove that next electron because Li plus is now in that noble gas core configuration. Okay, we look at beryllium. IE1, 0.9. IE2, 1.76. IE3, 14.85. Why that trend? Well, obviously, IE2 is going to be larger than IE1 because I'm trying to remove an extra electron from an ion already. But why the jump between IE2 and IE3? Well, if I remove 2 electrons away from beryllium, what's its electron configuration? Its electron configuration is helium. All right, so I've hit that noble gas core again. Look at boron, same thing. When I hit that noble gas core, or that ion that's isoelectronic with the noble gas, I get this huge jump in ionization energy. So it's always going to be more difficult to take those electrons away from the noble gas configuration. That's what we're dealing with when dealing with ionization energies. So let's look at a different view of this where we plotted these things out, and we're going to see another little trend that we have to worry about. Okay, so if I look at helium, right below that in the same line, that was the hydrogen. Okay, so the lower energies are those alkali metals. As I go across a row, I'm going to the noble gases. So if I look at a periodic table, let's start with lithium. Lithium's a low energy. Go across the row, I go from lithium, the next dot there's beryllium, the next dot is boron. So as we go from beryllium to boron, there's a sudden dip. It's actually easier to remove an electron away from boron than it is beryllium. Why is that? Well, with beryllium's got a fully filled S shell. So that helps stabilize it. It's happy. It doesn't want to give up an electron. So it's a slightly more difficult to remove that electron than it is from boron, which has got the 2s2, 2p1 configuration. So boron's willing to give up that p1. Okay, now as I go from boron, the next dot up is carbon, then nitrogen, and then oxygen. As I go from nitrogen and oxygen, I see another dip. Why is it more difficult to pull an electron away from nitrogen than it is from oxygen? Well, with nitrogen, I have a half-filled p shell. Because I have that half-filled p shell, it helps stabilize it. So it doesn't want to give up one of its electrons because it's happy being half-filled. It will, we can force it to, but it's harder to do that than it is to remove it from the oxygen, which has one electron it's willing to give up to get to half-filled. Okay, and then we continue on from oxygen to fluorine to neon. The noble gases always have the highest first ionization energies in a row because they really don't want to give up electrons. They're already stable. So a thing to keep in mind when we're looking at these first ionization energies, we're going to see those slight decreases in all of these rows when we get to that half-filled S subshell. So when we go from that half-filled S subshell to the next one, there's going to be a dip because that half-filled S subshell is going to be stabilized. See it with the half-filled P subshell. We see it with the fully filled P subshell, the noble gases. Okay, so looking at across a row, that's the trend we're going to see. Notice once we hit the transition metals, though, when we get to the transition metals, those first ionization energies pretty much flatline. Remember, with those first ionization energies, we're removing the outermost electrons first. Well, for transition metals in the same row, their outermost electrons are going to be those S electrons. So they're all going to have the same valence electrons that are being pulled away. So they're going to have relatively the same first ionization energy. That's why it kind of flatlines at those transition metals. All right, the other thing to note, if you look as we go from helium to xenon, that would be going down the noble gas core group. It's harder to remove an electron from helium than it is from xenon. Why is that? Well, xenon has more electrons in it, so because it has so many more electrons, there's physically more electrons there, which means they have to move further and further out. We're going to have a larger radius associated with it, which means those outermost electrons, those valence electrons, are going to be further away from that nucleus. They're going to be easier to remove. Whereas helium has fewer electrons, they're really close to the nucleus, they're going to be more difficult to remove. Okay, so another trend to look at is that first ionization energy is going to decrease as you go down a group. All right, so typically as we go across a row, across a period, we're going to get an increase in ionization energies, except for those dips at the fully filled S, half-filled P, fully filled P. As we go down a group, down a column, we're going to get a decrease in first ionization energy. Well, that one's easy enough. If we go down a group, we get a larger atomic radius because we're getting more and more electrons added onto that atom as we go down a group. So because we have more and more electrons, a larger radius, it's going to be easier to take one of those electrons away. Okay, another thing we have to consider is something called electron affinity. Electron affinity is going to be basically how willing a neutral atom is going to accept an electron. Ionization energy was forming cations. Electron affinity is going to be dealing with forming anions. Problem with this is these are going to be exothermic processes, which means when we look at electron affinities, they're going to be reported out as negative values. Or more importantly, the more negative the value, the more willing the atom is to accept an electron. Okay. For example, if we look at fluorine over here, it's a negative 328. Well, fluorine wants to form an F minus. Right? What about lithium? Well, lithium wants to form a +1. It wants to lose an electron. It doesn't really want to gain an electron, so it's got a less negative value. Okay, so the more negative the value, the more willing the atom is to accept an electron. That's dealing with electron affinity. We see the same trends that we saw with ionization energy, though, in that at a fully filled S, they don't want to change the number of electrons. They're happy there. Okay, so for beryllium, it doesn't want an extra electron. It's actually going to be a positive value. Okay, we'd actually have to force the electron on. If we go to the half-filled P subshell at nitrogen, it's got a positive value. It doesn't want extra electrons. And then as we get to neon, it's got a positive value. It doesn't want that extra electron. We can still force those on, but it doesn't really want them. And that's true across the row. As we go down a group, you can see those values in general get more positive. In other words, the electron affinity decreases as we go down a group. It gets harder and harder to put that extra electron on to a larger atom. Why? Well, same reason why it was easier to pull an electron off. We've got more electrons in a larger atom. We've got that larger radius. So putting another electron in there means it's got to compete with all those other electrons that are there. So we're going to get a lot more repulsive forces. So it doesn't really want that extra electron. Okay, so electron affinity is how willing a neutral atom is going to accept an electron. Think in terms of how willing it's going to want to form an anion. Okay, the more negative the value in this table, the higher the electron affinity. Okay, so we had some basic overall trends dealing with atomic size, ionization energy, electron affinity. We could predict those things and predict trends just using a periodic table. Now, there were exceptions to those trends that we need to know. We also need to know the reason why these trends occur. We can't just simply memorize, oh, atomic size increases as I go from right to left and down the periodic table. Yes, we need to know that to predict the general trend, but more importantly, we need to know why does that happen. So the last thing we're going to look at are going to be trends in metallic character. This is going to be real simple in that if you think about it, left-hand side of the periodic table, those are where the metals are at. Right-hand side, where the non-metals are at. Mainly as we go down a group, we get more metallic character. As we go from left to right across the periodic table, we get less metallic character. Why? Well, we're going from metals to non-metals. As we go into the non-metals obviously have less metallic character, so it's a pretty easy trend to predict. All right, but that's going to take us to the end of these periodic trends.